All right, I think we're ready to go. Awesome, we can get the recording started and then we can begin. So welcome to the Coulomb Counter webinar. My name is Luke Thomas. I'm an FAE at Dialog Semiconductor, and I'll be walking you through the webinar. This is the Coulomb Counter, so we're going to be taking a brief look at it, kind of getting an intuitive view of what it's actually doing, and then looking at a little bit more of the technical definition of it. So it's based off of app note 1171, which you can find on our website, and there's going to be a link at the end of the slideshow that you can click on for further reading. This is going to be sent to you via email, so you can always go back to these slides and see what's going on. So we'll do a quick introduction, then I'm going to look at the motivation of why you'd want a Coulomb counter. I'll try to give you a little bit of an intuitive understanding of what's going on with our particular Coulomb counter. Take a look at the technical understanding, so actually seeing what's going on with the equations and the capacitors. And then we're going to look at the GreenPAK's implementation of it, how we do it with GreenPAK, and what advantages that provides. And then we'll have a quick conclusion. So let's get started. Now I want you to imagine that you have this awesome dream where in your dream you're able to buy a flying car. And this flying car, it's going to cut your commute in half, if not more. And you can go super fast, you can get anywhere you want to, and you don't have to worry about roads or anything. And there's only one catch. The salesman gives you this decision. You can have two choices. You can get either the Model S or the Model O. Now this is the exact same flying car. The only thing is that they only have one instrument, and you can only choose one instrument. So the Model S has a single irreplaceable fuel cell. It can go 500 kilometers. That's the distance it can go before it runs out of fuel. But its only instrument is a speedometer. Now contrast that with the Model O, which has also a single irreplaceable fuel cell. It can also go 500 kilometers, but its only instrument is the odometer. Now suppose that you're trying to keep yourself alive in your dream, and you didn't want to rocket out of the sky going 500 miles an hour. Then you're going to have to choose an instrument that's going to make this decision the easiest. So which is that going to be? And that's effectively what we're trying to do when we're determining the state of charge for a battery. So there's lots of ways that you can determine state of charge, but the Coulomb counter is effectively solving this problem, where you have a fuel cell or you have a device that's only going to last for a certain amount of time, and you want to make sure that you're not flying it whenever it runs out of gas. So determining the state of charge is the exact same thing. The state of charge of the battery is the state of charge that's left before it's going to die. And you don't want your battery to die while you're performing maybe a measurement or sending a Bluetooth packet or just processing in general. You're going to want to keep it alive, depending on the context in which you're working on. So it makes a lot of sense to know what the state of charge is of your battery. Now, how is this done? There's tons of ways that you can do this. Anywhere from a simple voltage measurement, if you just measure the voltage at a given time, I can give you a rough estimate of the state of charge because it's going to be descending. So the lower you go, the closer you'll be to the end of the state of charge. However, batteries have kind of weird discharge curves, and as we'll see, some of them have extremely flat discharge curves. There's a little bit more complicated setups you could do by measuring the ESR. So you could open up the circuit, have a fixed load, measure the ESR, and that's going to give you a more closed, but that's a little bit more circuitry, a little bit more complicated. You could have lookup tables, you could have experimental measurement. Maybe you run 100 batteries over the course of your system to measure the worst case length that it can live, and then use that as a standard measurement, and you say never going to let a battery be left in the field for longer than that shortest amount of time. Finally, you could do Coulomb counting, which is what we're going to look at today. So Coulomb counting gives this idea of counting each individual Coulomb, which is a measure of charge, and counting it as it comes out of the battery to understand what's been extracted from the battery in terms of fuel, in terms of juice that's left in it. And then with that, you can get an accurate idea of the state of charge, or how much charge is going to be left in it. Now, what we're looking at is typically going to be used with primary cells. So primary cell is a non-rechargeable cell. And you can see on the bottom left graph, there's going to be your rechargeable cells, which we're all familiar with, and then the non-rechargeable cells, which we're also pretty familiar with. So the non-rechargeable cells are going to give you higher energy density, which makes a lot of sense if you want to have a low current solution and you want to kind of put it off into space or wherever you want to keep it without having to do a lot of managing of it, you're not going to have to mess with recharging it all the time. So you're going to want something with higher energy density that's going to last longer. And less circuitry. So primary cells don't require all of the charging, discharging, safety things that a typical primary cell would, because there's just less back and forth that has to happen, and it's pretty simple. You can get away with a lot less circuitry. Now, some of these primary cells have extremely flat discharge curves. So if you look at this discharge curve to the right, a few of these cells have almost no voltage change as the hours that they can perform extends. Until the very end, they're going to drop off very significantly. So if you were trying to do a simple voltage measurement of these batteries, you would have close to no idea of what its state of charge is if you only measured the voltage, because the change in voltage is going to be so negligible compared to the state of charge that you're going to have no idea what's going on. So there needs to be another technique, a different way of measuring that. So what is a Coulomb counter? Definition is a feature or device that measures the accumulated energy added to and removed from a battery, allowing accurate estimates of battery charge level. In other words, it's going to count up all of the extracted energy so that you can tell how much charge is left in your battery. And in some ways, charge relates to time. So you can determine either how much time you have left if you have a constant load, or how many, I guess, packets or trips in the sense of the flying car. You're not going to want to take a 15-kilometer trip if you only have 10 kilometers left in your gas tank. So what are some synonyms to the Coulomb counter? They go by Coulomb counting, Coulomb counter, fuel gauge, gas gauge. All of these get tossed around as ideas that are doing or performing the exact same function of measuring the battery charge level. So what is the motivation? Well, if you think back to the illustration at the beginning, if you have a flying car and you're trying to not fly it into the ground, there's a lot of motivation to know exactly when you're going to run out of juice. So user feedback is a really important thing, and that's something that we all get from our smartphones all the time. Having this idea of knowing exactly how much battery is left in your phone. Maybe you're going to need to charge it overnight. Maybe you're going to need to charge it before you go out to a trip where you're not going to have a power source. So there's all sorts of feedbacks that allow you to give you make smart decisions based on the current level of the battery and kind of your estimation of how much power is going to be used, just typically or even worst case. Another motivator would be the ability to minimize field failures. So if these batteries are driving all of these flying cars all over the earth, and you want to make sure that you know when they're about to run out of battery so you can replace them, it's going to keep you from taking a trip that's actually going to end in your flying car on the ground. So that's going to remove a lot of failures from the field and help you manage different aspects. If you're running like a network of IoT nodes or something to that sort, where there's a fielded devices that are going to be actually in the way. Now I have an internet is unstable thing, so I don't know if there's anything I need to do about that, but I'll keep going. And so finally, you're going to need cost efficiency. This is going to help you from a cost perspective if you're able to know exactly when your batteries are going to end their life. So if you have a field of 100 nodes, and if you had to do an open control loop where you simply wait, say 100 hours before you replace all of the batteries, some of those batteries might have only been discharged to maybe 50% of their state of charge or 40% of their state of charge. And so you're going to lose all of that cost efficiency over if you could have waited till they got down to 10% on each individual field item and then replace those as needed. So you get a lot of cost efficiencies, and kind of understanding where your battery is in a state of charge can help you with these types of things. So now let's look at a couple of principles of operation. So how is this Coulomb counting actually done today, and what does it look like? So I'm going to go back to an illustration of a speedometer and an odometer. So the speedometer approach is this idea of continuously sampling your speed, in a sense. And then once you're sampling your speed, or rather your current, you can get a distance measurement by taking your speed multiplied by your time. So if you have a regular interval where you're taking speed measurements and you multiply those by the time intervals that you're taking them, you can extract out with math in a distance measurement. So if you're going 100 miles for 1 hour, you're going to know you've traveled a distance of 100 miles. Now the other approach is an odometer approach. So the odometer approach is just like the odometer in your car. It has a unit value, maybe a tenth of a mile or a mile, and it constantly increments up in distance each time you move that unit of distance. So if you're driving fast, or if you're driving slow, or if you're driving fast and slow then fast, the odometer simply just tracks all of that change and accumulates it into the output like you see here in an odometer value. So it updates periodically, and it doesn't require any math. It simply just works. As you spin the wheels, it's going to increment the odometer. And so that's how two of the principal approaches to Coulomb counting are currently done. So on the left, we have the speedometer approach of the Coulomb counter. Now what it's doing is it's checking the speed, and then it's extracting from the speed the distance. The way it checks the speed is using this ADC, and this ADC is actually reading from a current sense resistor. So the resistor is going to generate a voltage based on the current, and from that voltage we're going to know exactly how much current is going through the Coulomb counter at any given time. So if you set this R sense resistor pretty low, you can get fairly negligible power losses in higher power systems. And all you have to do is take this ADC, gain it up, have high bandwidth, and accumulate over time the digital value of your current at any given time, add it into your counter at an interval given by the RTC. So this might be every millisecond, might be every 100 microseconds, whatever it takes. Now one difficulty with this, as you might realize, is as your speed is changing, you have to be able to catch differences in speeds. So this is sampled, and it's going to miss some stuff, and it'll be discretized and kind of quantized into values based on how fast you're actually sampling the R sense resistor. Now for the typical BLE packet, you're going to have typically low current consumption, and then as you send out an actual packet, you're going to have high current consumption while the radio is on, and you're going to drop back down to low current consumption pretty quickly. Now the speedometer approach is going to have to be able to have a high enough bandwidth to determine all of those spikes in current as your load dynamically changes from different states, whether it's a low power mode or a transmit mode or receive mode. All these different states, they're going to have different speeds or current consumptions. Now the odometer approach is a little bit different. The odometer approach is going to have a cap in the middle between the battery and the load, and it's not going to let any charge pass directly from the battery to the load. It's going to use these FETs to never let that happen. But what it does in essence is it captures the charge that passes through this C1 and counts the amount of charge that gets passed from the battery to C1 and from C1 to C2. So as the charge migrates its way over to the load via this matrix of FETs, you're going to be able to count the amount of coulombs that get passed. And now these are the two approaches, and they're kind of easily split into the speedometer and odometer approach. So let's look a little bit more at the speedometer approach. So how does it work? It requires constant sampling. So this is what the RTC is for, and it's going to force the device to take regular samples in time, just as if you had a speedometer and you're trying to figure out how far you're going for a given trip. Maybe a city trip, you're stopping, you're starting. You're going to have to take each time, maybe every second, look at your speed and then write that down. And you're going to have high gain in order to minimize loss. So this R sense resistor is going to be significantly low, less than an ohm. And the higher it is, the greater voltage output it'll have, but the more power it's going to waste. And so you don't want to waste any power. You want to get it as low as you can. So the way to get it low is to just find a low R sense resistor and then increase the gain of this ADC. So there will be a buffer here in this ADC, and it'll allow you to measure really low voltage values. The problem with that is it's going to require your ADC to use a significant amount of power, so maybe 200 to 300 microamps. You're also going to need high bandwidth. So in order to minimize the error as you stop at a stop sign and accelerate into a 40-mile-an-hour highway, you're going to need to have high bandwidth to catch all of those differences in speed, essentially. So that also is going to require you to have even higher power ADC to capture not only the low voltage signaling, but the high bandwidth profile of a typical load as it has transients that spike or just variable loads. You're going to have a high enough bandwidth to capture all of that data, or you're going to be having errors in your system. Your battery is actually going to be either having more charge than you expect or less charge than you expect. And both of those have their comparative issues that you don't want to run into. And lastly, you have to mathematically integrate. So it's kind of like a discrete stepped integration where you sum over discrete steps, but there's a little bit of math involved, and you have to add in your counter over a given amount of time. So it's slightly more complicated in what it's doing. The bottom line is it's high power. This ADC, all of these analog configurable components are going to take up 200 to 300 microamps. Now, if your load is running at 1 or 2 milliamps, then that's going to be a significant portion of your load, where it just doesn't make a lot of sense to have this sort of Coulomb counter in a low load application. And that's why there's the other approach to Coulomb counting, which is the odometer approach. So I want to give a brief vision into what's kind of going on with this odometer approach and how it actually operates, how it actually works. So you're going to be, like I said, transferring charge from one to another. And I want you to think about it as a thought experiment. So suppose that you have this experiment you're running in science class. You have 2 beakers of water, and you're trying to determine how much water gets poured from the hose into the experiment. Now, this beaker 2 is going to have to constantly be pouring into the experiment to keep things going, keep the fire down. You don't want any fire. But beaker 1 you can use to transfer your water from the hose to the beaker. So there's a technique that you could use to actually accomplish this, and it would probably be a 2-phase approach. So in one phase, you'd probably fill up the beaker to some level, and then turn off the hose and start dumping the beaker 1 into beaker 2. And then you'll probably repeat that over and over and over again. And so if you measured how much water you put in beaker 1, and then you dumped all of that water into beaker 2, then you could effectively count how much water goes into your experiment by just counting how much you put into beaker 1 each time you dump it into beaker 2. Now, there's a couple of issues with capacitors here that I think will become apparent as we go farther along. But you can't quite dump all of the charge out of a capacitor like you could dump all of the water out of a beaker. So you also can't fill up the beaker completely full in a relatively smart amount of time compared to how often or how much you could fill up a beaker with water. So there's some limitations, and let's look at how you would actually approach those limitations. So beaker 1, you're probably going to fill up to a certain level, and say that's going to be the max level that you're gonna fill up to. So you don't want to fill up any higher than that. And once you find that you've been filled up to that level, you'll stop the water flow, and then you're going to take your beaker over to beaker 2, and you're going to start dumping it down. You're not going to dump it all the way out. You're going to dump it down so that it's down to this minimum level. And if you define this minimum and maximum level, you're going to be able to determine the volume of water that gets transferred each time you go back and forth between beakers. Now, if you can determine this kind of unit volume that's being transferred each time you go back and forth between beaker 1 and beaker 2, then you can start to kind of count the units. Maybe it's an ounce of water each time you go back and forth. So you can start counting your ounces as you dump your beaker 1 from this max fill line to this min fill line over and over and over again. And that's exactly what the Coulomb counter is doing, except electrically, using charge. So phase 1 is going to be when you're filling up the beaker, beaker 1. So one caveat is you're going to have to fill up beaker 1 to a certain level and always to the exact same level. So you're going to do that by using FETs. So these Q1, Q2 FETs are going to allow you to connect your battery to your capacitor. As you connect your battery, as you know, the high voltage on the battery is going to be begin dumping current into the capacitor, and the voltage on the capacitor, say it starts initially at 0, is going to rise until it reaches the max voltage. We're actually not going to let it do that. We're going to confine the capacitor to only reach a certain level. Once it's reached that max fill line, We're going to switch over to phase 2, where we disconnect both of the FETs, so we have a break before make, because we don't want any shoot through going to the load. And then we're going to connect Q2 to C2. So this high fill line is now going to be connected to capacitor 2, or the output cap, and we're going to dump all of our current, or all of our charge, into C2, and then we're going to discharge into the load until we reach this minimum fill line. So if we disengage beaker 1 right at the bottom of this fill line, then it's not gonna leave that bottom fill line very much. So as we fill it back up, which is going to happen pretty quickly, and then we recharge it or go back to phase 2, it's not going to have moved a lot. So this provides some level of regulation too. If we force this capacitor to only go between 2 voltage values, then we're going to have some inherent regulation as a kind of added benefit that comes along with this technique of forcing our beaker to a minimum and maximum value. And there's a lot of advantages to this too. If we fill it up randomly to a random minimum height and a maximum height, it's going to be hard to track how much charge we're actually putting into the device. But if we always force so that we only discharge to a minimum value and only fill to a maximum value, then we can know that there's going to be a unit amount of charge that gets transferred each time we go back and forth between the phases. So there are a few constraints to this, this way of approaching the Coulomb counting technique. So first, you must know how much you measure, or you simply have to measure the same amount each time. So what I was just talking about is you have to really kind of understand how much charge is being dumped each time, or you can't really count coulombs. The second thing is you're going to have to initially fill beaker 2. So probably in your system, everything is going to start at 0 voltage, and you're going to have to just dump over and over and over again. It's going to be pretty fast transfer to get all of your water from the hose to beaker 2. But once that happens, you're going to effectively hit a steady state operation where you're slowly going back and forth between dumping out beaker 2 and then filling it up quickly and then dumping it out again. Lastly, you have to keep up with demand of beaker 2. So suppose that your experiment, something caught fire and you just need a lot of water. If your beaker 1 can't fill up beaker 2 fast enough to keep up with the demand, there's going to be some problems. And the analogy with that is if you have loads that are too high that can't keep up with the output bypass cap, then there's going to be issues. So that's just something to think about as you're looking into this solution, is how much of load am I expecting, and what kind of tax can that take on C2. But it gets into a lot of complicated issues of what's the minimum voltage of your load. And so there's a lot of system level design decisions that have to be made when using this Coulomb counter. But the GreenPAK is extremely flexible, and it can allow for all of these different design decisions. Okay, so we've had a quick introduction. We looked at the motivation. I've given an intuitive understanding, kind of thinking about the water of the beakers and as you would pour it into this thought experiment. Now I want to look more at the technical side of understanding actually how much charge is being transferred and what the numbers look like. So we have this equation here that is describing the operation of the charge transfer. So we have, and this is the only equation that you really have to worry about. And this is to determine how much charge. So the end of the equation is the delta charge on our capacitor. And this equation is saying that if you have a capacitor that has a change in voltage, so VT1 minus VT0, these two voltages at different times, then that's going to equal the integral from time 0 to time 1 of all the current that's passed through it over time, which is effectively the change in charge. So for our instance, the C is going to be a constant scalar value that is set by your capacitor selection. And that's going to be set by the C1 capacitor up here. The second is going to be VT1. So we're going to set that in our circuit as the maximum charge voltage, or the maximum fill line. We're not going to fill our capacitor up past a voltage that we want it to be at. So that's going to be our max charge voltage. VT0 is going to be set as our circuit minimum charge voltage. So we don't want to discharge the capacitor past that voltage. Even though we could, we don't want to provide some regulation to the design. and then delta Q. So this is the output of our equation. If we plug in these values, we're going to get the amount of charge transferred from T0 to T1. So the output of the function is the integral of all currents from T0 to T1. However, if you can control T1 and, if you can control VT1 and VT0, the integral can be pre-computed, and you can count the amount of charge irrespective of time. And this is a really powerful outcome because we don't have to do any math. We don't have to do any approximate integration like the speedometer approach. All of this is built into the physics of the capacitor. So we don't have to worry about that. As long as we can guarantee that the voltages are maintained and the current or the capacitor doesn't change, which is fairly easy to do, then we can get a relatively accurate representation of the delta Q that's happening each charge transfer as it changes from this voltage to this voltage. So there's two premises that happen with this Coulomb counter. Premise one is, given this equation, if we can control VT1 and VT0, then we can count a unit division of charge sourced to the load. So the main point here is the unit division of charge. So as we go back and forth between our fill lines, we can know that there is a unit division of charge that's being dumped into the load each time that we switch phases. And that happens if we control VT1 and VT0. Premise two is, if we know both the width of the unit division and the capacity of the battery, we can determine the state of charge remaining on the battery. So if you know how much charge is being transferred each phase, and you know how much your battery has in terms of full charge of the battery, then you can determine the state of charge at any point, as long as you're constantly counting how much charge has been discharged off of that battery. So let's look at each of these premises individually. So premise one, if we can control VT1 and VT0, we can count a unit division of charge sourced to the load. How is that actually done using our Coulomb counter technique? So you're going to want to have two analog comparators, and these are effectively going to be your automatic fill lines. So as the voltage of C1 increases and then decreases, the output of these analog comparators are going to be toggling. So and then we're going to put them into our switch logic that's actually going to drive Q1 and Q2. So it's automatically going to be bouncing back and forth between what I've termed phase 1 and phase 2, where phase 1 is where Q1 is on and we're charging up C1, and phase 2 is where Q1 is off and Q2 is on, and we're discharging our transferred current into the load. So if we have some way to control those thresholds, namely analog comparators, then we can dictate premise one, such as VT1 and VT0 are always going to be contained to a known value so that we can build some assumptions off of that. Premise two is, if we know both the width and the width of the unit division and the capacity of the battery, we can determine the state of charge remaining on the battery. So back to our equation, let's plug in these numbers and see what we get. So C is a value that's not going to change. Let's suppose it's 100 microfarads. And we have two voltages that we want to regulate between. So we can choose a little over 2 volts, so 2016 millivolts, and just above 1.8 volts. So 1820 millivolts. Now if we set these as our thresholds in our analog comparators, and this is the capacitor value that is passing our charge back and forth, we're going to find this outcome. So if you do the math, you multiply all these together, you're going to get 19.6 microcoulombs. Now once you have determined your amount of transfer that's going to happen between each phase, then you can take the battery that you're going to have and then divide out how many counts you're going to need to count before that battery is essentially extinguished. So let's look at the GreenPAK implementation of how this works. We kind of looked at the high-level understanding of what's supposed to be going on. Now let's look at the specific implementation of GreenPAK as we have done it in the past and as we're working on it now. So here, VN, this is showing the GreenPAK schematic, and as you can see, it's extremely simple. The VN is going to be your battery, which is the source of all of the power. and it's going to be going through this FET right here. So VN0, Vout 0 is going to be a FET that's controlled internally with the GreenPAK. This bypass cap is just going to keep things level as you're discharging stuff. So here, VCAP is your C2 capacitor that's transferring all of the current, and all of these capacitor values can be tuned to your specific solution. So here we have 10 microfarad, 1 microfarad, 10 microfarad. So we're going to fill up this capacitor with charge until it reaches this analog comparator threshold here, which is on pin 15. And then it's going to switch back and forth the two FETs to toggle the transfer from either phase 1 being connected to the battery or phase 2 being connected to the load. So this is what the GreenPAK GUI schematic capture system looks like. So you can see blocks, you can see wires, you can see pins, and this is how all of the GreenPAK is designed. So it's extremely simple, extremely intuitive, and extremely low power. So this analog comparator here that's running between 2016 millivolts and 1820 millivolts is only running at a couple of microamps. So that's incredibly low power compared to the 200, 300 microamp Coulomb counting solutions on today's market that are doing the speedometer approach. So here we're going to have an analog comparator, which we're going to look at the properties in just a second, that's driving the rest of this switch logic. So here we have the switch logic that's powering the two integrated power FETs that I showed right here. So this is FET 0 and this is FET 1. So these two FETs are going to be powered by our switch logic. And then they're going to drive also this counter that's just counting the times we move from phase 1 to phase 2. If we count these phases, we also have an I2C block that allows us to read back all of the counted value. So as it increments naturally, you can go back in and read this value so you can determine the state of charge at any point in the battery's life cycle by a quick I2C read, which is really pretty cool and actually very, very simple. So let's look at each of these pieces individually to see what the GreenPAK's actually doing. So here we have our analog comparator, and if you click on the analog comparator, we have the different properties that you can select for this low power analog comparator. So what we've actually done, instead of having two analog comparators with different fill lines, we have one analog comparator with a large hysteresis value. So it's at 192 millivolts of hysteresis, and that's going to be big enough of a gap for us to change the transfer level as we go back and forth, and it's going to be constant. So we'll set the internal reference at about 2 volts, and then we'll have 200 millivolts of hysteresis, and that's going to give us our two threshold values of 2016 for VIH and 1824 for VIL. So this is really powering kind of the heart of the design of switching back and forth to phases. Now, the switch logic is going to be taken care of in these couple of blocks. So it's pretty simple. It's just a couple of RS latches with a couple of timing elements. So these are 5 microsecond, either falling edge or rising edge delays. And that's going to be a way for us to generate this timing here. So the switch logic is powering these two FETs so that we can switch back and forth between the battery and the load. So the ACMPs are going to dictate when we switch back and forth, and the switch logic is going to dictate which FET actually gets connected during which phase. So the charging and discharging is going to look like this diagram here. So as we turn on FET 0, as you can see, if you look really closely, there's a break before make. So we're going to turn off both FETs, and then we're going to turn on the charging FET. When we turn on the charging FET, the voltage is going to increase through an RC circuit until we get to the 2016 millivolts setting. When that threshold trips, we're going to switch back to the discharge. And suppose it's a fairly low load situation, we're going to slowly discharge that into our load until we drop below a certain voltage. As soon as it drops below this 1820 millivolts, we're going to turn the whole machine around, charge it back up, and repeat. And each time we go through this phase change, we're going to keep track of it in our counter. So our counter is just being a simple counter, 16 bits, and it's clocking each time that we change phases. And there's also this count out, so if you wanted to have a predefined time for it to set a flag or warn the system, you could do that with this pen. But you're going to read this with just a simple I2C command. So here I've shown what a random read command looks like. You're going to choose your control byte and word address that addresses your specific GreenPAK. The Coulomb counter has an I2C address. You're going to address that. Then you're going to address the actual data bits of where this count is stored. So you'll pull from memory A5 and A6, which corresponds to the count 0 counted value, which is going to be real time. So as it increments in real time, this value is going to be updated in real time. So if you ever want to pull the Coulomb counter for its state of charge, you could just request that via I2C, and you're going to get the real-time count in this counter. And then once you do that, you can do a little bit of math in your micro to determine how much charge you have left, or what the expected amount of charge is, or how many counts that you expect to have. From there, you can do a simple division to determine your state of charge. And that's it. It's that simple. You simply have a couple of capacitors externally that you put through 2 FETs, and you pass the charge. You have to understand how much charge is being passed through each time. If you do just a little bit of math and a little bit of control, you can fairly accurately determine how much charge has left your battery if you manage all of these premises well. So let's look at the GreenPAK Coulomb counter. Where does it fit well? So it typically fits well in small battery devices. So these are the kind of IoT nodes that are going to be sitting out and are having extremely low current consumption. And there's a reason for this. They also work well with primary cells that have high energy density and don't need to be recharged, because as you recharge them, you kind of lose the initial value of the battery state. And they're in situations when you need an accurate state of charge. So effectively, it's just measuring the state of charge. If you have a micro and a couple of capacitors with this GreenPAK, you can measure the state of charge. And then it has an extremely low I sub Q in active mode. So as it's measuring the current consumption of your load, whether that load is in the milliamps or the microamps, the Coulomb counter is not going to be loading down your system to waste your battery current consumption. So it's actually fairly less than 10 microamps. It's around 2 to 3 microamps to run this entire system and to accurately count for 16 bits. So this is going to count up to 65,536 counts. And you can actually chain these together to get over 1 million counts if you need. If you have a fairly larger battery, or if you're running with small capacitors, you can get a fairly large value of counts, and it's just going to take a few more I2C reads to get to that. So that's it. That's all I have. My name is Luke Thomas. I have my email here if you have any questions, or if you're interested in our Coulomb counter solution. We have boards available that are ready today if you want to test them out. You can send me an email. I can get you hooked up with those. There's also an app note. So if you click on the link as these slides get sent out, you can check out the app note. It went into a little bit different details than I did now. So if you want further reading, you can check that out. And as always, you can find us on dialogsemiconductor.com and go from there. So that's it. That's all I have. If there are any questions, I can field some questions, and if not, we'll be done. Thank you, guys.